V is equal to x omega. And what is V? V is the linear velocity of this element dx.
Yes, sir.
Okay, V is the linear velocity of this element dx. I have written all the things: linear velocity, angular velocity, and all the things. Okay, so we know that there will be the induced EMF in this wire. There will be the induced EMF in this wire.
Yes, sir.
What we will do now, we will just calculate the induced EMF first in this small element dx. Then we will do the integration and we will get total EMF across the ends of the wire. Simple. Okay. So I am just calculating induced EMF in length dx. And this derivation is very, very important also for the exam point of view. Dx. So dx element में कितना induced EMF होगा? Okay.
Okay, sir.
For that you should know what is the motional EMF. Motional EMF. So motional EMF formula is given by magnetic field in which the coil or the wire is placed and length of the wire and the velocity. Okay, and this velocity is the linear velocity. Okay, this velocity is the linear velocity. This thing you should know.
Okay, sir.
And because this is the small length, this is very, very, very small, infinitely small length of the wire. So the induced EMF will also be very, very small. That is, and here is minus sign also. Okay. This negative magnetic field is given as V. Magnetic field will also be given to you in your question or derivation.
Okay.
They will say a wire is rotating. A wire is rotating in a given magnetic field V and rotating with an angular velocity omega. Find the induced EMF across the ends of the wire. Simple. So V as a length is given, and this is V. Okay, and what is this V? X into omega. This V is X into omega, no? I have written here. Yeah. Now put X into omega here. So this dE, and this dE is the small EMF in the wire for the length dx. Okay.
Yes, sir.
This is minus V into L. Simple. X into omega. X into omega. Now the thing, we have done the physics part. Now from here the math parts will be started. So we have just calculated the small EMF or the EMF due to the length dx. But we want the total EMF due to the whole length of the wire. So what we will do? We will do the integration. So just integrate this equation with limits. We will integrate. So this is x, and from where to where the x is? X is from 0 to L. Here at the end, one end of the wire.
Yes,
at the one end of the wire, what is the value of this x? This x is variable. X is 0 at this point A, and at this point B, the x will be length of the wire L.
Yes, sir.
Okay. So I am just applying the limit from 0 to L. This is the integration. So this will become the EMF E. And now we will do the integration. This is VL. Take the constant terms out of the integration as we have done many times. So this magnetic field is constant. Length of the wire is also constant. Omega is also constant. So this will become VL into omega and integration of x into dx. Integration of x. Okay.
Yes.
Okay, just a minute. This L now we will put dx. Okay. Why dx? Because we are just calculating the EMF for this dx length.
Yes, sir.
Okay.
Okay.
We will put, because here is L na. Instead of this L, we will put dx. We are just calculating for this. So instead of this L, we will put dx. And then we will integrate it. Okay. So I have just taken this common, not this L. So we have V into omega and x dx. V into omega x dx. Minus V into omega x into dx, and limit is from 0 to L. Now integration you should know. You should know the integration, how to integrate the function. This thing you should know. 0 to L, and this is x into dx. What you will do now for this? This is x to the power 1 here. So when you will integrate it, it will just increase one power. This will become x square. This will
Yes, sir.
become x square and divide it by the power again.
2. Yes, sir.
Yeah, and limit, apply the limit. Limit is 0 to L.
0 to L.
Just I am giving one more question. Suppose this is 0 to L and this is x square into dx. Then here is square now, so here it will become cube.
X cube.
And here is 3 and you
Yes,
will
sir.
apply the limit 0
0
to
to
L.
L.
Yeah. So this half is the constant, this will be like this and this will become, first you will put the upper limit, this is known as the upper limit, this is known as
Yes,
the
sir.
lower limit,
Lower
but put
limit.
the upper limit, this will become, put L in x, this will become L square
L square. Yeah.
and put 0 into x square, then minus into 0 into x square, this will become 0 square. So you will have the integration half of L square only.
Okay,
3
sir.
omega.
Yes, sir.
This will become half of L square and this is your answer. V omega L square divided by 2. So there are n number of things in this derivation. You should know the integration. You should know what is motional EMF. You should know what is magnetic flux. Okay. You should know the concept of the angular velocity and the linear velocity. So there are certain number of things. Okay, no problem. So just take the screenshot and revise it properly. And I will again discuss this derivation uh, in the next chapter.
Okay, sir. So you can scroll up, sir.
Scroll up.
Yes.
Actually, this was your.
Okay.
This is not a topic. This is the, from here you take the screenshot.
All right. Done, sir.
Okay. Now got it the derivation 50%
Yes,
or 60%.
Yes, sir.
I am not saying you have got it 100%, but at least 50% you
Yes,
should
sir.
have 60%,
Yes.
70%.
Yes, sir.
Okay. So now we will come to our topic. Okay.
Yes. Okay, sir. Done, sir.
Now our topic is very easy today. Motion. This is the magnetic field. So magnetic dipole moment you should know. You should know what is magnetic dipole moment. You have a circular coil and this circular coil having a current I. This you should know, and having the number of turn n, A is the area of the coil. This is a circular coil, so area of the circle is given by pi r square. So the magnetic moment is equal to NIA.
Yes, sir.
And the direction of the magnetic moment is given by the right hand thumb rule.
Yes,
Just
sir.
curl your finger along the sense of current. Your thumb will give you the direction of the magnetic
Yeah.
moment.
Yes, sir.
So when you will curl your finger along the sense of current, curl your finger anti-clockwise. You will
Yes,
get
sir.
direction of the magnetic movement towards you. Something is
Yeah.
towards you means outward,
Outward. Yes, sir.
outwards. Okay.
Yes.
So this direction of magnetic movement will be outward like. So this concept you should know. And remember this point also. Uh, This point, this angular momentum. What is the angular momentum of a particle moving in a circle? Okay, and I have written the definition of the the node point of the Bohr's model. According to the Bohr's model, the orbital angular momentum of an electron is an integral multiple of h upon 2 pi. And here the charge of electron h is the Planck constant. All things are given. So
Yes,
now I will just drive a relation in between the angular momentum and the magnetic moment. Okay, so according to the Bohr's model, angular momentum is given by integral multiple of h upon 2 pi.
Yes, sir.
Integral multiple means this n is equal to 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2,
Okay,
3,
sir.
4, 5, 6. N will be the integer. Okay.
Okay, sir.
And this n equal to 1, 2, 3 represents the shells, like K shell, L shell, M shell. In chemistry, you have
Yes, sir.
shell. And this Bohr's model is for hydrogen and hydrogen-like atom. Hydrogen-like atom or hydrogen atom means hydrogen have the one electron only. Okay, so this
Yes,
Bohr's
sir.
model is valid for the species for having the one electron only. By the way, so we have the magnetic moment also for the electron. What is the magnetic moment for the electron? This EVR divided by 2. In the last class, I have discussed the magnetic moment revolving around the nucleus. The, the electron revolving around the nucleus having the
Yes, sir.
magnetic moment, charge on the electron, velocity of the electron, radius of the circular path divided by the 2. EVR divided by 2 simply. So this will EVR divided by 2. Just divide M by L. M by L. So your M is this EVR by 2.
Yes, sir.
And what is your L? L is NH upon 2 pi.
Yes, sir.
So now we will simplify this. This will become 2 pi divided by NH. This 2 and 2 will be cancel out.
Yes, sir.
Okay. One thing more. This M will be, this will be EVR pi by NH. EVR pi divided by NH, and here is L. Okay. And what is the angular momentum? MVR. L
Yes,
is
sir.
equal to MVR, so we will put MVR here.
Into MVS.
Okay, just a minute. Magnetic moment is this, and this is this. Okay, sorry. Actually, we have to put angular momentum here. I have directly put this value. Just a minute.
Yes.
Here we will put MVR. This is angular momentum, so here we will put MVR. This is EVR by 2 is M, and this L is MVR. Okay.
Okay, sir.
So now your R and R will be cancelled out. Your V and V will be cancelled out. Okay.
So E by M.
Yeah, E by M. This is the ratio you will get, M by L. So from here you can calculate now M. M is equal to E by M into L. And this L is given by, now we will use the Bohr's model. L is equal to NH upon 2 pi. L is equal to NH upon 2 pi. So your magnetic moment is given by NHE divided by 2 pi M. So this is your magnetic moment. And what is the N? N is the shell number. N equal to 1, N equal to 2, N equal to 3.
Yes, sir.
And minimum value of N is 1.
Yes, sir.
Minimum value of N is 1. So
Yes,
at
sir.
N equal to 1, you will get the minimum magnetic moment. You will get the minimum magnetic moment, and that magnetic moment is given by, simply put the value in this formula, N equal to 1. So this M is equal to 1. Instead of this N, I have put it the value 1. This is HE. This is HE. This is 2 pi M.
Yes, sir.
And your M will be HE divided by 2 pi M. This M is the minimum.
Okay, sir.
And this minimum magnetic moment for N is equal to 1 is known as the Bohr's magneton. Is known as the Bohr's magneton. Magneton. Volts magneton.
Okay, sir.
Okay, just copy this. Then we will discuss the torque on a current carrying coil.
Done, sir.
Okay.
Done, sir.
Okay, done. Okay.
Yes, sir.
So torque on a current carrying coil or loop. Torque on a current carrying coil or loop. So this is your coil ABCD. Okay.
Okay, sir.
And this is the magnetic field. Okay. This is
Okay,
the
sir.
magnetic field. Okay. See this. This is your coil. You can imagine this as your coil.
Yes, sir.
ABCD coil, rectangular coil you have, and magnetic field is along the. You can imagine this direction. You can suppose this direction as x direction. So your magnetic field is along x-axis,
Yes, sir.
along I cap. You can say I cap.
Yes, sir.
I cap is representing the x-axis,
X-axis. Yes.
J cap y-axis, K cap z-axis. So
Yes, sir.
your magnetic field is along x-axis. This is your magnetic field along the x-axis, and this is your coil.
Yes, sir.
So this is the plane of the coil. So what is here now? Your coil is placed like this. Okay,
Yes, sir.
the plane of the coil is like this, and your magnetic field is like this. So there will be some angle. There will be some angle in the magnetic field, in between the magnetic field and the plane of the coil. And this angle is this angle, na? This angle. See here. See here. Okay,
Yes, sir.
this angle. This angle is theta.
Yes, sir.
This angle is given by theta.
Okay.
So
Yeah. Yes.
theta is the angle between the magnetic field and the plane of the coil. So I am writing it. What is theta? This B representing the magnetic field and plane of coil. Plane of coil. And this is a rectangular coil. So two sides means this side is equal to this side, and this side is equal to this side. So AB is equal to, I have written here also, AB and CD is equal to B, AD and BC is equal to L. Now there is one more concept that I will use here, that I will tell you later, but this is the concept, the main concept we will use here. Force on a current carrying wire. So see this coil, in this coil there is a current I, and we
Yes, sir.
can just divide this coil into the 4 wires. Wire AB, BC, CD and DA. What we are doing, just we are calculating the first force on this coil, total force on this coil. We are dividing this coil into 4 wires, AB wire, BC wire, CD wire and DE wire. And you should know what is the force on a current carrying wire. Suppose this is the wire PQ of length L, making an angle theta with the magnetic field. So the current in this wire, not the current, the magnetic force on this wire is given by I L into V into sine theta. I into L into V into sine theta. Okay, and this force is perpendicular to the length, and this force is perpendicular to the magnetic field also. Okay.
Okay, sir.
Yeah. Just change here. This force is perpendicular to magnetic field, and this force also perpendicular to the length of the wire, already discussed from this cross product. Okay.
Yes.
Now we will calculate the total force on this coil ABCD. Total force on this coil ABCD we will calculate. So total force on the coil ABCD means force on AB, BC, CD and D. Okay.
Yes.
Force. Yeah. Total force is the force on wire AB Force on wire BC, CD, DA, DA. And this force is given by IBL sine theta. Okay.
Yes, sir.
IBL sine theta. Force on AB. Now see the wire AB on this. And formula, this formula you have in your mind. And what is AB? This is your AB.
Yes, sir.
And what is the length of the AB? B.
B. Yes, sir.
So force on this wire is current into magnetic field into length into sine theta. And what is theta? Theta is the angle
Angle B.
between this wire carrying a current in this direction and
Yes,
this
sir.
magnetic field.
Yes,
Okay.
sir.
So you will write I V instead of L. What you will put? V.
B. Yes,
V
sir.
is the length, na? So
Yeah, okay, sir.
I V into sine theta. Now for the direction you will apply the
Right
right hand rule. Right hand rule, yeah. Right hand rule. Just point your
Yes, sir.
along the direction of the current and curl towards the magnetic field. Curl towards the magnetic field is in this direction, in X direction.
Yeah,
So
yes, sir.
point your fingers along the direction of current and curl toward the magnetic field. So you will get the direction of the magnetic force in the upward direction along
Upward,
the
yes, sir.
positive y-axis. You will get for the
Yes, sir.
positive y-axis. I am just representing here. This force is in this direction. This force FAB. And this
Yes, sir.
FAB is along y-axis, means you will multiply this by j cap.
Yes, sir.
Okay. So here also you will multiply it with by j cap.
Yes, sir.
We have done when we are just calculating the magnetic field inward or outward. First we were calculating the magnitude of the magnetic field, and that we will multiply with the unit vector in that direction. So force is along the y-axis and unit vector along the y-axis is j cap. Simple. Now for the VC, for this VC, what will be the force for this VC?
For
Simply
BC,
you will apply this formula for this wire. Now this is the wire BC, na?
L,
For
sir.
this wire BC, the
Yeah.
force on this wire is given by this formula I into length into V into sine theta.
Yes, sir.
I into length into V into sine theta. And what is the theta here?
The
Your
angle
90 degree.
90
Theta will be
degree.
90 degree.
Yes, sir.
So here theta is equal to 90 degree. Theta is the angle between the length of the wire and the magnetic field. Here theta is equal to 90 degrees. See, this angle and this angle is 90 degrees.
Okay.
So you will apply again plus I is the current. Same current is flowing throughout the coil.
Yes, sir.
Same magnetic field in which the coil
Yes,
is
sir.
placed. Length is L this time.
Yes, sir.
This is the length L.
Yes, sir.
Now sine 90 you will put here. For the direction, what you will do? For the direction,
Right hand thumb rule.
right hand thumb rule. Point your fingers along the direction of the current. Point your
Yes, sir.
fingers along the direction of the current and curl towards the magnetic field.
Yes,
Curl
sir.
towards the magnetic field. So this thumb is towards me, means outward direction I will get. So the force this time will be in the outward direction for this wire VC.
So towards the magnetic field, right?
Yeah, towards the magnetic field along the x-axis, na? Just like
Yes,
this.
sir.
This is the plane of the coil is like this. Coil
Yes,
is
sir.
like this at some angle with the magnetic field. Just point your fingers along the direction of the current. Point your finger along the direction of the current and curl towards the magnetic field like this. So you will get
Yes, sir.
your thumb towards you, means outwards.
Yes, sir.
So this direction you will get FBC, and this FBC will be along positive J cap or negative J cap.
Negative J cap.
No, this is towards outwards, outward
Okay,
direction.
yes, sir. Yes, sir.
So
So,
positive J cap.
positive J.
So here also you will multiply, not J cap, positive K cap, na?
Sir, Y axis, right?
No. This thumb, na? Thumb is
Yes, sir.
coming towards you.
Okay, yes, sir.
So something is
Z
coming
axis.
out of the screen.
Yes,
So
sir.
the Z axis. So you will
Yes,
take
sir.
here
K cap.
K cap. Here also you will multiply with
K cap.
K cap. Now force on the wire CD. This is CD. Same thing.
Yes,
All
sir.
the things will remain same for CD. This will
Yes, sir.
become plus I V into V into
So
sine theta.
Yes, sir.
Now for the direction, what you will do?
Right hand.
Point your fingers towards the current.
Yes, sir.
Point your finger towards the current, and you will curl towards the magnetic field. So this is the current direction, and magnetic field is along the x-axis. This is the x-axis in this direction. In this direction, the x-axis is there, means the
Yes,
magnetic
sir.
field is there. So curl towards the magnetic field or
Yes, sir.
x-axis. So we will get downward direction of the
Downwards.
force.
Yes, sir. So,
So this is FCD,
yes, sir.
and for this is downward direction means negative
Negative
y-axis.
Y axis. Yes, sir.
So you will multiply it with minus J cap.
Minus J cap. Yes.
Now for this,
DA.
current, okay,
Yes,
current
sir.
is in this direction
Yes, sir.
for this wire AB.
Yes,
Current is in this direction and
Yes,
curl
sir.
towards the magnetic field. So you will get direction away from you, means inward direction you will get. Inward direction you will get. This is FAD, and here we will multiply with it with minus K cap. For this you will multiply with J cap. This is for
Yes, sir.
CD, na? For
Yes, sir.
CD, this is the force IVV sine theta, and direction of CV. For the direction of CV, you will multiply with minus J cap.
Minus J cap.
Okay. For AD, the current is I, magnetic field is B, and theta is 90 degree again.
Yes, sir.
Theta is 90 degree. So this will become IVV, matlab ILV.
Sin 90.
ILV you can write, or IVL you can write.
Okay, sir.
IVL sine 90, and this is K cap, minus K cap. Now this is IVV sine theta, this is IVV sine theta, and this is J cap, and this is minus J cap. This will be cancelled out whole. Okay.
Okay, sir.
This is IVL sine 90 K cap. This
Yes,
is
sir.
IVL sine 90 minus K cap.
Yeah, cancel it.
So the net force on the current carrying coil in the magnetic field is 0.
0.
So you can write net force on a current carrying loop is 0 in uniform magnetic field. In uniform magnetic field. So force is 0. Now we will calculate the torque. So for the torque, you should understand what is torque. Torque is represented by tau. Like in the for the linear motion, the force is responsible, and for the rotational motion, the torque is responsible. Torque is responsible. So torque is given by force multiplied by perpendicular distance from the axis of rotation. For example, this is some rod, and this rod, on this rod there is one force F1 in this direction, another force F2 in this direction. So this rod is rotating about this point, okay, O. This distance is capital R and this distance is capital R. So what is the torque on this rod AB? Torque on this rod AB. First calculate the torque due to this force. Torque due to this force. So this will be force into perpendicular distance F1 into R. Okay. And this torque is in clockwise direction.
Yes, sir.
Now due to this force there will be another torque.
Yes, sir.
That is also given by force into perpendicular distance. But negative or positive you will take this for the direction. You will see for the direction. So this torque is in anti-clockwise direction. This torque is also in the anti-clockwise direction. So
Sir,
see this force.
clockwise, right?
Oh, sorry. This is clockwise. Okay,
Yes, sir.
clockwise direction. So this force is trying to rotate this rod AB in the clockwise direction.
Yes,
This
sir.
force also trying to rotate this rod in the and in clockwise direction. So this will also F2 into R, and here we will use plus sign. So torque AB is given by F1 plus F2 into R.
Okay, sir.
Okay, now see the forces. This FAB and FCD forces are collinear.
Yes,
Collinear
sir.
means FAB and FCD forces are acting on the same line.
Yes,
Are
sir.
acting on the same line. So FAB and FCD are collinear. And if the forces are collinear, then due to those forces, there will be no torque. So no torque. Now to another force also there,
Sir.
FBC and FCD. FBC and FCD. So see this, the line of action of FBC and FCD is different. One force is acting like this, another force is acting like this. Okay, the
Yes.
line of action is different. What will happen? See, this is your coil. Okay, this is your coil, and one force is acting in the down in the inward direction like this.
Yes. Yes, sir.
Okay, on the coil, this is your coil, and one force is acting like this, another force is acting like this. Means line of action of both the forces are different. Line of both the forces is different, and so due to this, as the line of action of both the forces is different, so these forces will generate torque. So FVC and FDA are non-collinear. So torque will be generated due to these forces. Suppose same rod I am taking AB. Same rod I am taking AB. This is your rod AB. Again I am taking. And one force on this rod is like this. And one force is like this. Now will this rod AB will rotate or not? This torque will not rotate, or you can say there will be no torque on this rod AB. Why? Because F1 and F2 are collinear. Collinear means they have a same line of action.
Yes, sir. Yes, sir.
So here in this case you can say no torque. So due to the force FBC and FCD, the torque will be there, and that torque we have to calculate. So now see this figure. See this figure. This force is BC force. This force is AD force. So what I will do, I will just draw a parallel line like this. Okay. Here separately I am just making the figure for FAD and for FBC. So this will look like this. This is your FBC. This is your FDA or AD.
Yes, sir.
Okay, and this is your angle theta, because this is the plane of the coil. This is the plane of the coil, and here is the magnetic field. This is the direction of the magnetic field.
Yes.
In this direction, the magnetic field is there, and this is plane of coil. Okay, so torque we have calculated due to the two forces having different line of action. Okay, so here the total torque will be sum of the forces and the perpendicular distance from the axis of rotation. Okay, either you can calculate like this, or you can just calculate like this.
Okay, sir.
So imagine this coil is rotating about this axis. Okay, here is one axis like this. Here is one axis, and about this axis the coil is rotating.
Yes, sir.
Now perpendicular distance of this force dA from the axis of rotation will be this. This will be the perpendicular distance, and here in this case this will be the perpendicular distance. So this angle is also theta. This whole length is B, small b. This is V now. So this will
Yes,
be
sir.
also V when you will join this. So this whole length is V. So this will be V by 2, and this will be V by 2. From the trigonometry, you will get this distance V by 2 sine theta. This distance V by 2 sine theta. How you will get this? This distance you have V by 2. This angle is theta, and you want this distance AB.
Yes, sir.
Suppose this is the ABC triangle. So just a minute. Wait, I'm just waiting for the azan.
Okay, sir.
Suppose you have this triangle. This triangle you have taken this, and this, and we want this distance b by 2 sine theta. How? Now this is sine theta, this will be cos theta.
Okay, sir.
B by 2 cos theta. So this is your b by 2, this AC is b by 2, and we want to calculate the AB. So cos theta is base divided by hypotenuse for a right angle triangle. So here this is the theta, opposite to this theta this will be perpendicular, and this AB will be base. So cos theta is AB and hypotenuse is b by 2. So from here you can get AB, and your AB will be b by 2 cos theta. So here I have written this distance with the help of the right angle triangle. I have just calculated this distance. Okay.
Okay, sir.
Now we can calculate the torque. We can calculate the torque. Torque is the force into perpendicular distance from the axis of rotation. So torque due to the force VC and dA is given by, first calculate the torque due to the one force. Due to the force VC, calculate the torque. So right here force, that is FVC. Okay, FVC, and perpendicular distance from the axis of rotation, this is b by 2 cos theta.
Yes.
Now this torque will try to rotate the coil in this direction like this. Okay. Like this, the coil will rotate like this.
Anti-clockwise.
Yeah, anti-clockwise means this force from here will try to rotate the coil like this.
Yes.
And this force will try to rotate the coil like this. So the coil will rotate anti-clockwise.
Yes.
So both the forces are trying to rotate the coil anti-clockwise. So here means both the torque will be added up. Okay, torque due to this force and torque due to this force will be added up, because both the torque are trying to rotate the coil in anti-clockwise direction. So torque due to this force FDA is given by FDA into b by 2 cos theta. B by 2 cos theta. Now take b by 2 cos theta common. Here you will have FBC plus FDA. Now see what is the value of FVC and FDA. From here we will get FBC. This is your FBC.
Yes, sir.
IBL sin 90.
Yes, sir.
FDA. So DA last force, this IBL
IBL.
sin 90 again.
Yes, sir.
I am not talking about this vector. Why? Because I am just calculating the magnitude. This is the magnitude only, and here FVC is representing the magnitude only. Okay, so here
Okay,
I will write again IBL sin 90, and sin 90 is
1, sir.
1.
Yes.
So this will become into, this will become 2 IBL. IBL was simple. IBL and sin 90 is 1. This is IBL. This is IBL. IBL and IBL is 2
So
IBL.
2 IBL, yes.
And this 2 and 2 will be cancel out. So
Yes,
finally
sir.
you will have a torque is equal to I LB into capital B and cos theta. Okay. Remember one thing. What is L into V? Area
Yes, sir.
of coil. And what is I into A? Magnetic moment
Yes, sir.
for N equal to 1. If the number of turn is 1, then magnetic moment is given by IA. So this torque, this is I and LV is A, this is V and this is cos theta. Now simply you can write here, for this IA you can put M and this is V and this is cos theta. So torque is given by MV cos theta. Torque on a current carrying coil due to the magnetic field is given by MV cos theta. And
Cos
what is
theta.
theta? Theta is the angle between the
Angle
magnetic
between.
field and
Yes.
the plane of the coil.
Okay, sir.
And the plane of the coil. But we want to calculate this torque. We are interested to calculate this torque in terms of the angle between the magnetic moment and the magnetic field. Magnetic moment and the magnetic field. Now again I am taking the same coil. This is the same coil ABCD. Same coil ABCD, and here you have magnetic field and here you have the magnetic moment. And this is the line, and this magnetic moment is making an angle of 90 degree because magnetic moment, direction of the magnetic moment is always perpendicular to the plane of the coil. So that is why this magnetic moment is making an angle 90 degree with the coil, and this is your magnetic field. This magnetic field is making an angle of theta with the plane of the coil. Ziyad, getting this thing?
Sir, can you repeat it again, sir?
Okay. Actually, the concept of magnetic moment should be clear. See here, this is your coil. Okay,
Yes.
this is your coil, and I have told you the direction of the magnetic moment will be perpendicular to, always perpendicular to the plane of the coil. So this
Yes,
pen representing the magnetic moment.
Okay, sir.
Okay, so magnetic moment will always be perpendicular, and magnetic field is making an angle theta with the plane of the coil. Simple. We already know na magnetic field is making an angle theta
Yes,
with the
sir.
plane of the coil.
Yes, sir. Yes.
Say here. Yes. Okay. So, and now suppose alpha is the angle. Alpha is the angle between the magnetic moment and the magnetic field. Angle between magnetic moment.
So can we choose beta?
Of course, you can choose beta also.
Okay.
But alpha in books you will find alpha everywhere, alpha. So why we can choose beta? We can choose instead of beta, gamma. It's your choice. You can choose any of the angle. But
Okay,
for
sir.
the formula, everywhere you will get alpha. So you will get confused sometime why you have taken the beta also.
Okay.
Okay. But
Okay,
you
sir.
can choose. This is your choice. Okay. So here is
Okay.
alpha. So now see this alpha plus beta is equal to 90 degree. This alpha, alpha plus theta is equal to 90 degree.
Yes, sir.
Because this is the straight line. If
Yes,
you
sir.
are not getting why alpha plus theta is equal to 90 degree, see this is the straight line. And
Yes, sir.
angle, all the angles, sum of the all the angles on the straight line is equal to 180 degree. So see all the angles. This is 90 plus alpha plus theta is equal to 180 degree. So 90 plus alpha plus theta is equal to 180. See, this is your straight line.
Yes,
Sum
sir.
of all the angles on the straight line is equal to 180 degree.
Yes, sir.
So this angle is 90, alpha and theta is equal to this is 180 degree. So from here, we will calculate the alpha. So this will become 180 minus 90 minus theta.
Yes,
So
sir.
your alpha will be 90 minus theta.
Yes, sir.
Put the value of alpha. Actually, this is also true. This is also true, but we will calculate theta.
Okay, sir.
This is 180
By 9.
minus 90
minus
minus alpha. Theta is equal to 90
90.
minus alpha. So this is your theta.
Yes.
Now you will put this theta in the equation number 1.
Okay, sir.
Put theta is equal to 90 minus alpha in equation number 1. So torque is equal to mv sine instead of theta we will put 90 minus alpha, and sine 90 minus alpha is equal to what I am doing today. So mv cos theta is there.
Cos theta. Yes, sir.
Yeah. This is torque. This is mv. This is cos.
Cos
Instead of this theta, we will
90
put
minus
90
alpha.
minus alpha,
Yes, sir.
and cos 90 minus alpha is equal to sine alpha.
Yes.
If it is written sine 90 minus alpha, then you have to write cos alpha.
Cos alpha. Yes,
These
sir.
are the trigonometric relations. So cos 90 minus alpha is equal to sine alpha, and this is your final formula mv sine alpha. What is m? Magnetic
This one.
movement.
Yes, sir.
Magnetic movement. See, this is the torque on the coil.
Yes, sir.
M is the magnetic moment
Magnet.
of coil. Alpha तो पता ही है, angle between the
Yes, sir.
magnetic moment and beta.
Yes. Yes, sir.
So mv sine alpha. This is looking like something else. This is like alpha. So this is the torque on a coil, and this torque is for the coil having one turn only. If the coil have n number of turns, then we will multiply this with n. So you can write here, if coil have capital N turns,
Yes.
in that case your torque will be n mv. You will multiply the whole torque with capital N mv sine alpha. Simple. Okay, just take the screenshot of this derivation, and in this derivation there are n number of things.
Yes.
Whenever you will do the derivation, there are certain number of things, like there can be the integration, there can be the direction, there can be
Yes,
the
sir.
calculation, there can be the trigonometry. Okay, just take the screenshot.
Yeah. Done, sir.
Okay. Done.
Yes, sir. Done, sir. Done, sir. Done, sir.
Okay.
Okay, done, sir.
So actually, na, this figure, this coil ABCD
Yes, sir.
and this coil ABCD both are same, and this I have shown here. Na, what is this? This is this part. This force VC, this force AD, and the length, this length. Okay, V. I have shown here. Okay,
Okay, sir.
so don't confuse him. Now we have simple cases. special cases we have. So we know what is torque now.
Yes.
MV sine alpha.
Yes, sir.
And alpha is the angle between the magnetic moment and the
Yes, sir.
magnetic field.
Yes, sir.
So case 1, magnetic moment is perpendicular to the plane of the coil, or magnetic field is in the plane of the coil. Okay. So magnetic moment perpendicular to the plane of the coil means what is the value of alpha? 90 degree,
Yes, sir.
because magnetic moment is perpendicular to the
Yes,
magnetic
sir.
field.
Yes, sir.
So here we have, this is the magnetic moment, suppose,
Okay, sir.
and this magnetic moment is perpendicular to the magnetic field. So you will put here alpha MV sine 90. Instead of alpha, we will put 90 degree. So this will be the maximum torque. That is MV. Because sine 90 is the maximum value of sine. Now second case. If the magnetic moment and the magnetic field are in the same direction. So in this case, the alpha is equal to 0 degree. So torque is MV sine alpha. Torque is equal to MV sine 0. What is the value of sine 0? Sine 0 is 0.
Zero.
What
Yeah.
you should do now? What you should do? Take a notebook, a small notebook,
Okay,
and
sir.
write the mathematical things there. Means like that, like you again and again you are forgetting what is sine 90 and what is sine 0. So write there sine 90, sine 0,
Okay, sir.
and some mathematical concept, like if you know don't know the differentiation, if in between I am just telling you the differentiation part. Suppose I am telling you that part that is not related to the 12th syllabus, like torque. Torque is a topic that you have studied in the rotational motion in 11th class 1 year ago. So
Yes, sir.
those topics you should write in your that notebook so that you can remember that. See here, here is the magnetic field in this direction and magnetic moment is in this direction. So magnetic field and the magnetic moment are in the opposite direction. So the value of alpha in this case will be 180 degree,
Yes,
and
sir.
the torque is given by mv sine 180 degree, and
Yes, sir.
sine 180 degree is again 0. Okay. So this will equal to 0 because okay, copy this.
Done, sir. Done, sir.
Okay, done.
Yes.
There is one question from NCERT, that is example number 4.11. So no need to, okay, you can take the screenshot. Good.
Okay, sir.
This is not very hard or tough question. This is very easy question. 4 parts are there in this question, A, B, C, D. Okay. So this is from the chapter number 4, moving charges and magnetism, NCERT, and example number 4.11. If you have NCERT, you will get this question. So this is based on the torque on the current carrying coil, and there are some concept used in this question that we have previously studied, like the magnetic field on the center of the circular coil carrying the current. I am just coming drinking water. So here a 100-ton closely wound circular coil of radius 10 centimeter carries a current of carries a current of 3.2 ampere. Okay, 3.2 ampere.
Okay, sir.
There is a circular coil, and that circular coil having the number of turns is equal to 100, and in that coil the current of 3.2 ampere is flowing. They are asking first part, A part. What is the field at the center of the coil? Field means magnetic field at the center of the coil.
Okay, sir.
Secondly, they are asking what is the magnetic moment of the coil. These two parts are very easy.
Okay, sir.
So suppose this is your coil. This is your coil, and this coil has a radius of 10 centimeter. No?
Yes, sir.
So radius of 10 centimeter. And current suppose flowing in this direction. I do not know the direction because direction is not given. So I am just taking this anti-clockwise. Current is
Okay,
of
sir.
3.2 ampere.
Yes, sir.
And number of turns is given.
100.
First part, what is the magnetic field at the center of the coil? We have a formula for the magnetic field at the center of the coil, that is given by mu naught I divided by 2R. This is the formula discussed here. We have this formula, na, mu naught I by 2R. I have made
Yes,
the
sir.
2 star also.
Yes,
So this
sir.
is a circular coil, and at the center of the circular coil having the current I. So at the center, the magnetic field is mu naught I by 2R.
Yes, sir.
So when you will put all the values, the value of mu naught is 4 pi into 10 to the power minus 7. And current is 3.2 ampere
Yes, sir.
divided by 2 into R. R is 10 centimeter. You will
Yes, sir.
convert this in meter.
0.10.
You will divide it by 100.
Yes, sir.
Okay. Divide it by 100. This will become 0.1.
0.10. Yeah, 0.
No, 0.10 also you can say.
Okay.
0.1 meter.
Yes. Okay.
And number of turns in the coil is 100.
Yes,
So you
sir.
will multiply this with 100, and here you will write mu in also, because
Okay.
for one turn the magnetic field is mu naught I by 2R. For n turns, mu naught I n by 2R. You will multiply n with the given magnetic field for the one coil. So when you will calculate, this value will come out to V2 into 10 to the power minus 3 Tesla. And talking about the direction, if you will just take the direction, because the current direction of the current is not given, so I will not talk about the direction. If this will be the direction, if this will be the direction of the current, if
Yes,
then
sir.
you will apply your right hand thumb rule,
Yes,
curl
sir.
your finger along the sense of current. The
Yes,
direction of the thumb will give you the direction of the magnetic field at the center of the coil. So direction will be outward. Direction of the
Outwards.
magnetic field will be outwards
Yes, sir.
if the direction of the current is given.
Okay, sir.
So this is your A part. For B part, they are saying what is the magnetic moment of this coil? Magnetic moment. Formula of the magnetic moment is M is equal to NIA.
Yes, sir.
N is 100. Current is 3.2 ampere.
Yes, sir.
Now area of the circle, pi r square. pi into 0.1 square. This is area of the circle is pi r square, very simple. So this will be
Yes.
come out to be 10 unit of current is ampere and meter square. This is 10 ampere meter square. Okay. And for the direction of the
Okay, sir.
magnetic moment, again you will apply the right hand thumb rule.
Yes,
Curl
sir.
your finger along the sense of current, the direction of the thumb will give you the
Yes.
direction of the magnetic moment.
Yes.
Now C part. They are saying now the coil is placed in a vertical plane and is free to rotate about the horizontal axis, which coincides with its diameter. A uniform magnetic field of 2 Tesla in the horizontal direction exists such that initially the axis of the coil is in the direction of the magnetic field. So you have a coil and there is a magnetic field in the horizontal direction and your coil is in the vertical plane. So this is the condition for the C part. This is your coil and here is the magnetic field, this direction. This is your magnetic field. Okay. And axis of the coil is this. This is the axis of the coil. And after that they are saying initially a uniform magnetic field of 2 Tesla is in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. The coil rotates through an angle of 90 degree. The coil rotates through an angle of 90 degree under the influence of the magnetic field. Under the influence of the magnetic field, what are the magnitudes of the torques on the coil in the initial and the final position? Initial condition of the coil is this. Okay, initial condition of the coil is this. Okay, so the magnetic field is along the axis of the coil. Okay, is along the axis of the coil.
Okay, sir.
Yeah, and this is the axis coinciding with the diameter of the coil. So we have to calculate the torque on this coil in this position. So the magnetic moment will also be in this direction. Why? Because magnetic moment will always perpendicular to the plane of the coil. So this is your plane of the coil and this is the magnetic moment.
Yes, sir.
Because magnetic moment, I have told you, this is your coil and your magnetic moment will be this always perpendicular to the plane of the coil. So here what will be the alpha? 0 degree. What is alpha? Alpha is the angle between the magnetic moment and the magnetic field. For
Yes, sir.
calculating the torque, we have the formula, na?
Yes, sir.
mv sin alpha.
Yes, sir.
So torque will be magnetic moment, we have magnetic field, we have 2 Tesla,
Yes, sir.
but sin 0 is 0.
Yes, sir.
So you will put here alpha 0 and sin 0 is 0. So your torque will be 0 in this case. Now when you have rotated this coil 90 degree like this is your
Yes,
initial
sir.
condition of the coil. Now you have rotated this coil 90 degree. So this coil will become like this.
Yes, sir.
This will become like this.
Yes, sir.
And in this case, the magnetic field will remain same.
Yes, sir.
Along the horizontal direction, the magnetic field will be there. But this time your magnetic moment will be 90 degree because earlier your coil is like this, means
Yes, sir.
like this. So your magnetic moment will be like this.
Yes, sir.
Now your coil will be like this. Your
Yes, sir.
coil will be like this, rotated 90 degrees. So the magnetic moment now will be like this, perpendicular to the plane of the coil.
Yes, sir.
So magnetic moment will be like this. See. So this is your magnetic moment. Now this time the alpha is equal to 90 degree. And we have seen that when alpha is equal to 90 degrees, the torque on the coil will be maximum. Torque is given by mv sine 90. And this torque is the maximum torque. And this is given by mv only. Now you will calculate this magnetic moment. You have 10. Magnetic field you have 2. So this will become 20 Newton meter. Newton meter is the unit of torque, SI unit of torque.
Yes.
Okay, note down this. The last part, now we do not have the time because I am having the next class. So last part we will discuss in the next class.
Okay. So can you scroll down? Done, sir. Done, sir.
Okay. So D part, we will continue from the D part tomorrow.
Okay, sir.
Okay, Ziyad. Thank you.
Thank you.